Hello, and welcome to Linear Algebra. This is lecture 35 on determinants. So last time, we talked about the spectral theorems. For self-adjoint matrices, so Hermitian matrices, and also for normal matrices. This time, we're starting a new topic, new chapter in the book, determinants. And today, we want to focus on existence and uniqueness. Okay, so as you're probably all aware, the determinant is a function that takes in a matrix and gives you back a number. So in this chapter, we're going back to working with arbitrary fields. So F here is any field. If you prefer to think of the real numbers and the complex numbers, that's fine, but this also works for F2 or FP, for any prime P. And the most important property is that it tells us when a matrix is invertible. Right? So a matrix A is invertible if and only if its determinant is not 0. So one way of thinking about that is it tells you that the matrix is invertible if and only if its determinant is an invertible element of the field. All right, and said in that way, this extends beyond fields to rings, but that's beyond the scope of this course. So the case that we've actually seen before, and we didn't call it the determinant, is the case of 2x2 matrices, right? So the determinant of a 2x2 matrix is just AD minus BC. And let's keep this case in mind as we discuss the definition. So here are some properties of matrices, sorry, of functions from matrices to numbers, to elements of the field. We say that a function is alternating if it vanishes if two columns of the matrix coincide. Right, so for example, the 2x2 determinant has this property because if you have a column that repeats, then you would get AC minus AC, and so 0. Right? We're going to say that a function from matrices to elements of the field is multilinear if it is linear in each column. Right? So it means that you think of it as a function of the columns of the matrix, and when you fix all of the columns except for one, then it is linear in that. So this is just like the inner product is linear in the first entry. That means if you fix the second entry, then you get a linear function of the first entry. So to the determinant, or a function from matrices to a field, is called multilinear if when you fix all of the columns save one, then it is linear in that column. So for example, for the 2x2 determinant, this says that if I take a linear combination of two vectors and make that the first column, but I fix the second one, then if I work this out, I would get A1 plus EA2 times D minus B C1 plus EC2. And I can write that as the determinant of when I have the first column A1, C1, plus E times the determinant of when I have as first column A2, C2. Right, so that's linearity in the first column. And similarly, if I fix the first column, but take a linear combination of vectors for the second column, then, right, if you write this out, you would get A D1 plus E D2 minus B1 plus E B2 times C. And if you write that out, you can recognize it as the determinant of AC B1 D1 plus E times the determinant of AC B2 D2. Right, so that is multilinearity for the 2 by 2 determinant. And then the final property we're going to want to have for functions from matrices to elements of the field is just that it be normalized. So this says that the value of the function when you evaluate it on the identity is 1. So we're going to want the determinant of the identity matrix to be equal to 1. We say that a function from matrices to elements of the field is normalized if it has this property. And so let's check that our ongoing example, the 2 by 2 determinant, does have this property. So the determinant of the identity matrix is indeed 1. Okay, so these 3 properties give us our definition. So at the moment, we'll say a determinant function, but part of the purpose of this lecture is to show that there is only one. So this will be a function, let's call it D for the moment. So D sub n from n by n matrices with entries in the field F to the field F. That is alternating. Multilinear and normalized. Okay, so what we've checked when going over what these words mean is that the 2 by 2 determinant is indeed a determinant function. And the purpose, or one of the main goals of today's lecture, is to prove the existence and uniqueness theorem. That says that for every natural number, there is one and only one. Determinant function on n by n matrices. Okay, so a very useful tool in proving existence and uniqueness is to notice that if you have the first 2 properties, alternating and multilinear, then you already have something that's a lot like a determinant function. So if D is an alternating multilinear function, right, defined on n by n matrices. So first, if D sends the identity matrix to 0, then D is just identically 0. It's the 0 function. It assigns 0 to all n by n matrices. Okay, so why is this true? Well, it is a multilinear function. So if I take every column and I write it as a linear combination of the standard basis, then I can expand this function D in terms of, I can pull out the coefficients and just be left with, in that column, elements of the standard basis. And I can do this for every column. So D of A for any multilinear function, it can be written as some huge sum where the coefficients involve a bunch of the entries of the matrix, and all of the columns are elements of the standard basis. Now, if you repeat elements of the standard basis, then for an alternating function, it has to vanish. So that means that the only terms that can contribute to D of A are when the elements of the standard basis that are the columns form a basis. Now, if you're an alternating function, then that means that when you switch two columns, the function switches sign, right? And that's easy to see because if you were to add column 1 to column 3 and put that as your first and third columns, then that would be 0 by alternating. But if you expand that out, that shows you that when you switch columns 1 and column 3, you switch sign. And same thing with the other ones. So when I have D of a matrix, and that matrix has columns making up the standard basis in some order, then putting them in the usual order just costs me a sign. So what I end up with is if D vanishes for the identity matrix, then D vanishes for every matrix, as long as I know that D is alternating and multilinear. On the other hand, if D is alternating multilinear, but it doesn't vanish on the identity matrix, then assuming the theorem, we can write D of A as D of the identity matrix times the determinant of A. Okay, so that's because what you could do, if D of the identity matrix is not 0, then you could take your function D and divide it by D of IN. And this would give you a alternating multilinear normalized function. So then if the theorem holds, if there is one and only one alternating multilinear normalized function, then this one is it. So you'd get the determinant. Okay, so let me mention this argument I gave perhaps a bit quickly here to say that DFA vanishes whenever D vanishes on the identity. A similar reasoning can be used to see that if you have any alternating multilinear function, then DFA is equal to 0 whenever A is singular, right? So if A is not an invertible matrix, then it's in the null space of any alternating multilinear function. Okay, so why is that? Well, if A is singular, and say we label the columns of A as alpha 1 through alpha n, then we know that the set alpha 1 through alpha n is linearly dependent. Right? We know that's equivalent to A being singular, A being not invertible. And since this is linearly dependent, we know that there is a alpha j, which is the linear combination of the other columns. Right? Say alpha j equal to the sum of a k not equal to j of ck alpha k, where ck are some constants. And so then what we can do, we can write d of a as d of the matrix, right? So I'm going to have alpha 1, whatever, and then so I have up to alpha j minus 1, and then instead of alpha j, I'm going to go ahead and write this linear combination then I would have alpha j plus 1, and so on up to alpha n. And then I can use multilinearity to write this as the linear combination of the values of d when I replace the jth column with just this alpha k. Right, but notice what we have here, k is not equal to j, and this matrix has as its jth column alpha k. So this column is repeated somewhere else, right? If k was over here, if k is equal to 1, then that column coincides with this one. So by the alternating property, all of those terms are equal to 0. Right, so here we used multilinear. Here we used alternating. But that establishes what we wanted. If A is singular, then D of A is equal to 0. Okay, here's a nice corollary of the existence and uniqueness. Which serves to show that knowing that there is only one lets you prove that it must have some nice properties. So in particular, the determinant of a product of matrices is equal to the product of the determinants. Okay, so let's prove this. Okay, so if A or B is singular, then so is their product, and so both sides are 0. Then both sides vanish. Okay, so let's assume A and B are invertible. And let's fix A. Fix A and consider the function d sub a, it goes from n by n matrices to the field. And what this does is you give me a matrix B, any matrix B, and I give you back determinant of A times B. Okay, so let's think of this as just a function of arbitrary matrices. Right? Okay, notice that D of A applied to a matrix B, right? So let's think about this in terms of the columns. So the columns of B, let's call them beta 1 through beta n. Then D sub A of this would be the determinant of A times B. And if you multiply A times B, you get a matrix whose columns are A beta 1 through A beta n. Okay, so the fact that the determinant is alternating implies that D sub A is alternating. Right? If two columns here coincide, then two columns over here are going to coincide. So this function would vanish, and hence this function would vanish. Similarly, the fact that the determinant is multilinear implies that D sub A is multilinear. Right? Because if one of these columns is a linear combination of the other ones, then because if I can write one of these columns as a linear combination of some vectors, then over here I'm going to get A times that linear combination. But because A is linear, that is a linear combination of the images under A of those vectors. And so then multilinearity here gives us multilinearity over here. Putting these together, we see that D sub A is alternating multilinear. So D sub A of B is equal to D sub A of I times determinant of B for every B in NNF but that tells us the determinant of AB, which is D sub A of B, is equal to D sub A of I times determinant of B, which is equal to determinant of A times the determinant of B, like we wanted. Okay, another corollary of existence and uniqueness. So if A and B are similar, then determinant of A is equal to, actually before that, let's do invertible. So if A is an invertible matrix, then its determinant is not zero and vice versa. Moreover, in that case, if A is invertible, then the determinant of the inverse is equal to the inverse of the determinant. Okay, well, we already know that if A is singular, then the determinant of A is equal to zero. So we just need to show that if A is invertible, then the determinant of A is not equal to 0. If A is invertible, then 1 is equal to the determinant of the identity matrix, but the identity matrix I can write as A times A inverse. And then because the determinant of product is the product of the determinants, that is equal to determinant of A times the determinant of A inverse. Right? Hence, well, the determinant of A is not equal to 0, right? Because the product of these two numbers is equal to 1. And solving for the determinant of A inverse, we get the determinant of A inverse. Right, just as we wanted. Right, and then a further corollary, again from existence uniqueness, is that if A and B are similar matrices, then they have the same determinant. Right, so this shows that the determinant of the matrix is an invariant of that matrix. Right, the proof is very straightforward. If B, so if they're similar, then I can write B as S times A times S inverse for some invertible n by n matrix. Then the determinant of B is equal to the determinant of SA S inverse, which by the last couple of corollaries, I can write as determinant of S times determinant of A times determinant of S inverse. And now the determinant of S and determinant of S inverse cancel, and I end up with just the determinant of A as required. Okay, so these corollaries show that as soon as you have existence uniqueness, you have some of the main properties of the determinant. So let's focus now on existence and uniqueness. Okay, so let's start by proving existence. By induction on N. We already know for N equal to 2, right? Because we wrote out the formula and checked that it satisfies all three properties. For N equal to 2, for N equal to 1, it's really trivial, right? If you have a 1 by 1 matrix, then whatever entry you have, that is the determinant. And it's immediate to check that it satisfies the three properties. So suppose inductively that we have a determinant function b n minus 1 from matrices of size n minus 1, square matrices of size n minus 1 to the field. And let's use this determinant function to define a determinant on matrices of size n by n. So here's what we'll do. Given a matrix of size n by n, where n is at least 2, let's let capital Aij of size n minus 1 times n minus 1 be the matrix obtained from A by removing the ith row and the jth column. So for example, if A is a 3 by 3 matrix, then A1, 2, so this tells us remove the first row and the second column, right? So remove the first row and the second column. So you're left with E, F, G, F. Right, and let's do one more. If we did 2, 3, A2, 3, then you would remove the second row and the third column. You have A, B, G, H. Okay, so that's a way of getting n by n square matrices from a matrix of size n. Let's fix an index I, and let's define d sub n, right? So this would be a function on matrices of size n by n valued in the field. And so what it will do is it assigns to a matrix A sum j goes from 1 to n of -1 to the I plus j, aij, dn-1 of capital Aij. Okay, so lowercase aij is just the entry of the matrix A in the spot ij, and then this is the matrix where you've removed the ith row, jth column. It's a matrix of size n-1 times n-1, and so we can apply this function to it. Okay, and now we want to show that this is a determinant function. Right, so right now we're just proving existence. We're not worried about uniqueness. We want to show that this is a determinant function. So that means we need to check that it is alternating, multilinear, and normalized. Right, so let's start with multilinear. So let's say you have a matrix A with columns alpha 1 through alpha n. And say that one of those columns is a linear combination of two vectors, call them beta and gamma. So here, beta and gamma are vectors in Fn, and E is just a scalar. Okay, so let's let B, capital B, be the matrix you get by replacing the kth column with beta, and let's let C be similarly the matrix you get from A by replacing the kth column with gamma. Right, so we want to show that dn of A is equal to dn of B plus E times dn of C. Right, that's what multilinearity means here. Or K is just some arbitrary, alpha K is an arbitrary column of the matrix A. Okay, so the thing to notice that AST is equal to BST is equal to CST. So here I'm looking at the entries of the matrices unless T is equal to K. So if you're not looking at the kth column, then all of the entries of A, B, and C coincide. So correspondingly, we have capital AIK is equal to capital B I K. Actually, here, let me just think about it. L. Capital A LK is equal to capital B LK. It's equal to capital C LK for all L. Right, because if you're removing the kth column, then there's no difference between the matrices. Finally, we want to notice that if J is not equal to K, then Dn minus 1 of A Lj is equal to Dn minus 1 of Blj plus E times Dn minus 1 of Clj. So if you remove the kth column, then these matrices are the same. On the other hand, if you remove the jth column where J is different from K, then the kth column of A, which is this linear combination, that survives after you remove the jth column, and the corresponding column of this matrix is a linear combination of the columns of these matrices. And so by multilinearity of Dn minus 1, we have this equality. So with these observations, we see that Dn of A, right? So remember, Dn of A by definition is going to be the sum j goes from 1 to n of minus 1 to the I plus j, little a ij, Dn minus 1 of capital A ij. Okay, so in this sum, we're going to separate out the term when j is equal to k and the terms when j is not equal to k, right? So I can write this sum of the terms where j is not equal to k, and there what we're going to do is if j is not equal to k, then we have this property, right? This I should have said also is for all L. We have this property, so in particular, Dn minus 1 of Aij is equal to Dn minus 1 of Bij plus E times Dn minus 1 of Cij. Okay, so that takes care of all of the terms of this sum where j is not equal to k. So all that's left is the term where j is equal to k. Let me put that down here. So when j is equal to k, I would get minus 1 to the I plus k, little a I k, little a I k, I know exactly what that is. That is little b I k plus E times little c I k, and then capital Dn minus 1 of capital A I k. Okay, perfect. So this just uses our observations. Now, I want to write this. I want to avoid using A altogether. I want to use B and C instead, right? So I can write this first term, this first sum. I'm going to write this sum j goes 1 to k minus 1 to the I plus j. So I have the Aij with Bn minus 1 Bij plus, and then common factor of E, sum j different from k of minus 1 to the I plus j, Aij, Bn minus 1 Cij. Right, so let me do this in 2 steps. So first, right now, I'm just going to separate this out into terms with B and terms with C. Okay, and so now what I'm going to do, I'm going to write the same thing, but this aij, because j is different from k, that is the same as bij. And the same thing when I get to aij over here, because j is different from k, aij is the same as cij. And then over here, because j is equal to k, capital aik is the same as capital bik. And same thing with c, capital D, capital A I K is equal to capital C I K. Okay, wonderful. Now we stare. And we notice that this sum plus this term gives us the function dn of b. And then this sum plus this term gives us the function dn of c. And we have what we wanted to show. This function d sub n is multilinear. Okay, next let's show that this function d sub n is alternating. Right, so if capital A is alpha 1 has columns alpha 1 through alpha n, and let's say the two columns coincide, say alpha k is equal to alpha l, then capital Aij has two equal columns as long as j is not in KL. So dn minus 1 of capital Aij is equal to 0 if j is not in KL. Hence, capital D sub n of A is equal to, well, by definitions, the sum j goes from 1 to n of minus 1 to the I plus j. Remember, I is something fixed, some fixed index. Little aij, dn minus 1 of capital Aij. Now, in this sum, everybody dies except when j is k or l. So I'm going to have two terms. So the term when j is equal to k and the term when j is equal to L. Okay, now because those two columns are the same, alpha k is equal to alpha L, then little a I k is the same as little a I L. So I can write this as, let's say, a common factor of minus 1 to the I plus k, a I k, and that's adding dn minus 1. That's multiplying dn minus 1 capital Aik plus minus 1 dl minus k capital dn minus 1 AIL. Okay, and counting column swaps, this vanishes. So this matrix and this matrix have the exact same columns, except possibly for the order, right? So because A has two repeated columns, alpha k and alpha L, and here I've removed alpha k, and here I've removed alpha L, right? So this matrix and this matrix have the exact same columns. They just might be in a different order, right? Now, the alternating property, as we talked about earlier, it tells you that if you switch two columns, you only change the function by a sign. So you can think about how you go from this matrix to this matrix by changing the order of the columns, and you'll find that the number of sign changes make this vanish. Okay, so I'll let you think about that. I recommend just looking at the 3x3 case, for example, to see how it works, but it works the same way in general. And that shows that dn is alternating. So finally, we need to check that it is normalized. So I need to check that its value on the identity matrix is just 1. So by definition, this would be the sum j goes from 1 to n of -1 I plus j, and here I'll put a delta ij, dn minus 1 of capital I sub j. So the entries of the identity matrix are often denoted delta ij, so it's also known as the Kronecker delta. This is equal to 0 if I is not equal to j, and it's equal to 1 if I is equal to j. So that means that here only one term survives. We end up with -1 to the I plus I, and then the delta ij is just 1, and then we have dn minus 1 of I of the n minus 1 identity matrix. And because dn minus 1 is normalized, that's just equal to 1. So altogether, we just get 1. Right, this establishes existence will also prove uniqueness by induction. Okay, so for n equal to 1, uniqueness is immediate, right? The only possible normalized function, normalized and linear function, is just the identity, just the determinant function of a 1-by-1 matrix is just whatever the entry is. So let's assume there is only one determinant function dn minus 1 on matrices, square matrices of size n minus 1. We need to show that any determinant function on matrices of size n by n is determined by dn minus 1. Okay. Now we know that any alternating multilinear function vanishes on singular matrices. So it's enough to focus on dn of A for A invertible. Okay, so since we have an invertible matrix, by taking linear combinations of columns And using multilinearity, it's enough to compute dn of A for matrices A of the form. Okay, so you have some matrix of size n minus 1 times n minus 1. You have zeros here and then a 1. And then over here, who knows? You have some fixed, well, some vector size n minus 1, right? So if you give me any n by n matrix and it is invertible, then by taking linear combinations of the columns, we can arrange for the final row to just be zeros and then a 1. Right, this might involve switching the order of columns. I'm okay with that. And but you can get to something that looks like this. So if you can compute dn of A for matrices that look like this, then you can compute dn of A for arbitrary matrices, just using alternating and multilinear. Okay, so let's define a function using that. So the function, let's go with curly E, n minus 1. So it's going to take a matrix of size n minus 1 and give us back a number. So what we want to do is, you give me a matrix B, I will just put it here. I'll keep these constants, right? Fixed constants, I don't care what they are, but let's say they're there. Take this function, right? So, oh, sorry, that's not a function, that's a matrix. So what I mean is take dn minus 1 of that function, of that matrix, right? So now it's a function, now you get back a number. Okay, but now it's easy to see that this function is alternating and multilinear. If you start with the identity matrix, the n minus 1 times n minus 1 identity matrix, then you would have dn minus 1 of the identity, zeros on the bottom, and these constants, whatever they are, over here. But then using the first n minus 1 columns to take linear combinations, you can get rid of these constants. So you would end up with dn. You would end up with dn of in minus 1, zeros, 1, zeros, zeros. And this is just the n by n identity matrix, and dn is the determinant function, so that's equal to 1. So great, so now we have a function that is alternating and multilinear on functions, on matrices of size n minus 1. And it's equal to 1 on the identity. So we know that this on an arbitrary function matrix B is equal to this evaluated on the identity times the determinant, well, times dn minus 1, because that one we know is unique, of B. And so we just show that this was equal to the identity, is to 1, this is equal to dn minus 1 of B. Thus, we've shown that dn of A is equal to dn minus 1 of A prime, right? Where A prime is the matrix in the upper left block of this, and the n is determined by dn minus 1, right? So if you have a unique determinant function on n minus 1 size square matrices, then you have a unique determinant function on matrices of size n by n. Right? So that finishes existence and uniqueness, and we'll pick up from there next time.